So we are going to go ahead and answer one question from section 1, 2, that's solving systems by Gaussian elimination. And then we are going to go ahead and do matrix algebra today. So step item 1 that we are going to do is problem 15 from 1, 2, and then we are going to go to section 1, 3. We are going to talk about matrix algebra. Matrix algebra is we are going to be beginning to play with matrices and see how to add, subtract, and multiply them. Okay, so here is the topics: addition, subtraction, and multiplication of matrices are going to be talked about. Problem 15, it's saying that go ahead and apply Gaussian elimination to the system. 2y plus z is equal to 8 minus x plus 3y minus 2z is equal to 1, and 3x plus 4y minus 7z is equal to 10. Of course, we want to use the matrix version just to get ready with matrices. So 1, 2, 1, 8, minus 1, 3, minus 2, 1, and 3, 4, minus 7, 10. So it's a good practice to double check before we dive into this thing to make sure all of our entries are correct, and so we don't have entry problem. Okay, looks like we are on the right track. Now, the Gaussian elimination, we said we proceed in 2 stages. Stage 1 is so-called forward elimination. Which culminates in an echelon form. And then in that next stage we identify free variables and move them to the right. And then at the very end we do the so-called back substitution. This is a small problem, so perhaps we are not going to see all of these things so explicitly, but the ideas are all the same. So in the forward elimination stage, we aim for the following entities. At least those guys got to go away. Perhaps more stuff is going to go away, but we don't know ahead of time what's going to happen without doing the work. So if I want to eliminate this minus 1, first of all, I notice that I do have a pivot. This 1 is as good as a pivot as anything else, and there is no reason to exchange these things. Now, in practice, in actual computing practices, they always bring the biggest guy to the pivot location. We are going to talk about those practical considerations later on, but right now we are kind of closer to hand calculations. Hand calculations, 1 is actually a friendly number, doesn't create problems for us. If we were to move 3 up here, it makes our life actually a little bit harder. So at any rate, so this is going to be our pivot, first non-zero entry of that row. It's going to be used to remove items below it. So to remove this item, what do I need to do? Yeah, you just simply add the 2 of them, and that is going to be our new row 2. And to kill this 3 here, what do I do? Minus 3 row 1 plus row 3. That's going to also remove that entry from row 3. So I continue here. So first row stays put. Adding these 2 creates a 0. What do I have? 5 minus 1. What else? 9. We are adding them. So then minus 3 times that plus this better give me a 0, which it does. yes, -2, -10, and -24 and 10 is -14. So we succeeded in making these guys to go away. Next issue is to move forward and make this guy go away. How do we do that? We say that again. Yes. If you wish to think about it in 2 steps. If this number was 1, our life would have been a lot easier. Is that right? So that tells me when I take row 2, first divide it by 5. Dividing it by 5 makes this to become 1. To get rid of this -2, I need 2 in this location. So I multiply by a 2. If I take 2/5 of row 2 and add it to row 3, the result is going to be just what I want. Now notice how this was created. This is the entry. So let's analyze this creature that we see here. This is negative of the entry to be eliminated divided by the pivot that we are using to eliminate that entry. So take that number, make it negative, so if this -2 becomes +2, divide it by 5, so that we are going to call that a multiplier, times R2, the row on which the pivot is sitting, plus the row on which you want to cancel the entry. We apply this thing. So 1, 2, 1, 8 stay put. We are going to have 0, 5, -1, 9, 0. Now 2/5 of 5 is a 2, and -2 is going to give us the 0 that we want. How about the other entries? So is it 2/5 of this entry minus 2/5? 2/5 of -1 is -2/5. I have to add row 3 to it, which is -10. So I take a common denominator, 5, this is -2, and the -50. So it becomes -52/5. Do the same thing with 9. So I have to take 2/5 of 9 and add to it -14 that I have. So you said 18/5 minus 14. Again, take a common denominator. And that one, luckily, looks like I have -52/5 again. Is that right? Okay. Now we succeeded in our aim of getting rid of these entries, making our matrix in this format. Turned out to be nicely triangular form. So when it is like that, everybody is going to be a dependent variable. We don't have any free variables to move to the other side. So all that we have to do now is to do what? To apply back substitution. So now we are at this stage. So it turned out, in this problem, it turned out that we didn't have free variables anyway to move to the right hand side. We do the back substitution. So very last row we start at that one, and what do we do with that? Essentially, if you wish to think about it, you have -52/5 of z is equal to -52/5. What do? You divide by the coefficient that you have, or if you wish, you so you have a lot of choices to apply right now. Let me go back. It was x, y, z, is that right? You have a lot of choices. You can still continue and apply the Gaussian elimination steps, or you can convert back to the traditional style and write it like that. Since the book uses this strategy, I use the same thing, but you could use Gaussian elimination and completely do away with the x, y, z's. So step by step, This one tells me z is equal to what? Yeah, z is equal to 1. I move back up here. That tells me the 5y minus 1 is equal to 9. So 5y is equal to 10. So who is my y? 2. Moving back to the very first equation, I have x plus 2y plus z is equal to 8, which tells me x is equal to 3. So in this case, our equation has a unique solution. If you want to figure out what does that mean geometrically, those of you who have taken calculus 2 or perhaps beginning of calculus 3 might be able to answer that question. What do each of these equations represent? What? Somebody said it? No. Three-dimensional? No. No, it's not a line. What is it? It's a plane. It's a plane. So each of these things is a plane, like the roof, the ceiling, and that wall, then that back wall. The three of them intersect at that corner. So these could be three planes in space at kind of arbitrary looking angles, and they happen to collide at just one point. No two of them are parallel to each other. They collide, and they give you one unique solution, which is what we found here. Okay, so that is one example. Now let's move ahead and do some stuff from section 1-3. If you have more questions, remember you have tutoring, office hours, and you can always bring it up next class time. So we are in section 1-3. We are going to talk about algebra of matrices. What do you mean algebra of matrices? Or in mathematics is a standard tradition that you just go ahead and define certain pieces, like pieces of a game, and then you kind of set your rules as to what you're going to do with these pieces. Just like pieces of a chess or something like that, we play the same way. In mathematics, things that are important for us, things that look like the basic operations we have seen in elementary school: addition, subtraction, multiplication, division. Then you come to middle school, you have exponentiation. So basic operation that we have in mind are these things. And here's a notation for exponentiation or power. You go into calculus, then you have also composition. So we want to talk about these things. This is going to be the easy part of it. This is going to be substantially much more complicated. Then this is going to be even more complicated than that. And so we are going to take our time when we are going to talk about multiplication and division. Division is going to be entire chapters by itself. So let's just go ahead with addition and subtraction. Okay, justification or a procedure for adding matrices is not going to be all that complicated. Suppose you are a store manager and you have kept your tallies for how much sales you have made in month of May, June, July, and so on. And then you have some entries that perhaps in month of May you have sold $10 million. In month of July you have sold $11 million. June and July have sales of $7 million. And these are the entries, say, for some year, and then you have some entries for the next year. Maybe you started doing very well on May, and then well, if you have entries like these, those entries begin to give you an idea of a matrix. If you have a rectangular array of numbers, you already are dealing with matrices. You might not call them matrices, you might just call them tables of numbers and such, but they are matrices. What can you do with them? If you want to compare this May compared to the previous May, well, you can subtract them to see how much extra you sold. So you can say that minus this is 5. And then you can compare each month. Now you can take these things as array of numbers and then perhaps let's see, minus and then plus. That is going to tell you how much extra you sold in 2010 compared to 2009. You just do what comes naturally, that is, you subtract the components from each other and you get some entry. So this year you sold 5 million extra in May, you had a loss of 1 million on June and a gain of 2 million in July, and so on. So addition and subtraction of matrices is a very simple concept. The way we do it is that we say we apply these concepts to the entries, or we say we are going to do them component wise. Now before we go any further and talk about multiplication, let's fix our definition for what we mean by matrix and how we are going to refer to it. So a matrix is a rectangular array of numbers. Obviously it has rows and columns. First thing that we want to talk about is what's the size of a matrix. When you want to refer to a matrix, you want to say how big the table is. The size of a matrix is written as number of rows with the multiplication sign followed by number of columns. So if I talk about a 2 by 3, so I read this as 2 by 3, I mean a matrix that has 2 rows and it has 3 columns. Now some numbers will be written in these locations. Let's, for the sake of discussion, suppose I have 5, 3, 7, 9, 10, and 20 these locations. Each of these things are going to be referred to as an entry. Now we typically need to mention where does a certain entry sit. So we are going to number our location or cells in the following way. We are going to mention the row number, so we have row, and here are the columns. This is row 1, column 1. This is row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, row 2, column 3. So essentially, keep in mind that we say row first and then column next. Same style as here, which we mentioned how many rows we got by how many columns we got. Now, most often we need to talk about matrices in general. So if I have a matrix and I want to call the matrix A, and I want to talk about its entries, but I don't want to tie myself to specific numbers, I use the lowercase of the same uppercase letter we used for the matrix, and then I put my indices or my location here. If my matrix is small, which every single problem that you see in this course, they are small, then you don't need to put a comma. Of course, if I had a matrix if I didn't put a comma here, it wouldn't make good sense, because it could have been 102nd row and 3rd column, or it could have been a 10th row and 23rd column. But we are not dealing with matrices that big, so if you don't put a comma here, it doesn't hurt. It's not going to be confusing. So we write A11, we really mean A1 comma 1, A12, A13, A21, A22, A23. So that is how we refer to each of these entries. Now we might go even more general than this. We might talk about M by N matrix. So in this case we have 2 rows and 3 columns, but of course I could have any number of rows and any number of columns. Since I am not specifying how many rows I got, then I am forced into a situation like this. I say this is row 1, 1, 1. So this is second row, column 1. So on I go until I reach the last row. If my row is called to be row number M, then I'll have AM1. Okay, so depending on how many rows you got, the index of the last entry here is going to be integrated by that. Now you tell me how to call the entries on this row. I'll have A21, and then so on it goes. Oh, already made a mistake. Column.
Put 1 in front too.
It is one day. Wrong coffee. Okay. So what should I write? 1, 2. There we go. So maybe I need my amount practice. 1, 3, and so on we go. And the last one is going to be A1N. Who is the bottom right entry here? AMN. Now in this mess, sometimes we need to take a look at a particular row and a column. It's traditional to refer to the row by letter I, column by letter J, and then target the entry that is sitting here. How is that going to be referred to? A, I, J. Okay, so that would be a general notation for our matrix. More often we are just dealing with the specific matrices. What do we want to do with these matrices? First thing that we want to do is talk about addition of 2 matrices. What do we mean by A plus B? So we said in that case we do what comes naturally. You just add corresponding entries. So let's just practice. Suppose I have, let me write down easy numbers. So addition of matrices, nothing mysterious about it. Corresponding entries get added up. So what am I going to have here? 102, 203, 304, and so on. Same story with subtraction. And this is also component-wise. Now, if I had a situation like 2, 3, 4, 5 minus 1, 2, what do I do then? This is undefined, truly undefined. When we are doing matrix activities, we need that the matrices to be compatible. They have to have certain restrictions on their dimensions for the thing to work out. So this is undefined because matrices are not so I don't know, this is supposed to be dealing with the first column or second column or what. So we have to always have the compatibility requirement in back of our mind. Now if I am dealing with matrices, there are certain ideas you have learned back in elementary school which are still applicable. If I am adding three things, if I have multiple operations to do, there is always a question of which one of them do you do first. Okay? Like the standard thing that happens when you are running a project is what do I do first? Well, if you are adding a bunch of numbers, you know from way back when that it doesn't make a difference, but that was dictated by certain laws which are still applicable here. So if you had to add three numbers, you could have said, okay, add the first two and then add the third one. And somebody might have asked you, well, why don't you add the last two and then add the first one? And you say that they are the same by, there was a name attached to that law. You remember what? Say it again. No, commutative means A plus B. If you are adding two matrices, it doesn't matter who you go with first, so this one you call it commutative. It doesn't matter all that much what you call it, so long as you remember that that idea was there. This one was what? Associative. So we have those laws. What else we have? Okay, we want to talk about distributive law, but that requires another concept, which is multiplication. So let's start talking about multiplication of matrices. That's where things get interesting. First, let's do easy multiplication. Easy multiplication, well, back in algebra, how do you refer to A plus A? No, if we are adding them, so just 2A, is that right? So A plus A is just 2A, or if you had several of these things added, so this is 3 times A, and you don't write multiplication notation, so it's a triple A. Well, if I had a matrix, and so if I had a matrix, let's just pick arbitrary entries. If my matrix is A, B, C, D, what would the matrix 2A look like? Remember, this is just A plus A. So you have A, B, C, D, just add it to itself. What happens to every entry of it? It just doubles. So this kind of a multiplication does not come as any major surprise. Now when we have these two guys next to each other, we want to give them different kind of names to say, well, this is a simple thing and this is a complicated thing. And ordinary numbers that we knew already, they are given a name of a scalar. Scalar is just one number by itself, and this other one is a matrix. So what multiplication are we talking about? The multiplication that we are talking about is a scalar times a matrix. Scalar times a matrix has a very simple recipe. Multiply each entry of the matrix by the same scalar. So here we have a simple recipe. We multiply each entry by the same scalar. So if I had alpha times A, B, C, D, I define this to be what? So take that scalar, multiply by each entry of it. Okay, now that is the end of the easy life as far as multiplication goes. Past this point, things become interesting and also complicated. Let's see what is the complication. Let me just start by saying that the kind of multiplication that comes to your mind is a valid one, but typically not all that useful. Not so useful multiplication idea is the following. Suppose you had A, B, C, D, and then you had another matrix x, y, z, t. What would have been a naive way of, well, right now there's no reason to call it naive, but it's going to turn out to be a naive way of multiplying these two. Suppose I want to multiply these two matrices. Just a times x, b times y, c times z, d times t. We could do that, and some people actually make use of it some places, a few places here and there as a name also, but we are not going to really encounter it so much, so it's not given any kind of a prominence. We can't think of much to do with it. A more useful type as I explain it, you're going to say, well, why do you call it multiplication? Why don't you call some other name? And that's a standard problem in mathematics. The same word gets to be used to mean different kind of things. And you have to kind of get used to it. Let me give you an example. Suppose I go to the market and I buy 2 shirts and 3 pants and say 4 hats. And I pay $10 for each of these, and say $20 for each of those, and $30 for each of these ones. And I'm asking for total cost. Well, that's not a big issue. What do? It's 2 times 10 plus 3 times 20 plus 4 times the 30. So you say I had 20 and 60 and $120 to spend. I spent $200. So can I think about this as a kind of multiplication where I pick the number of things multiplied by the prices in a kind of a format that looks like a clean-cut multiplication? I say yes. I'm going to introduce some array of numbers. Here's 2, 3, 4, and the other array of numbers, 10, 20, 30, I'm going to take these 2 arrays. So here's one array, and here's another array. I want to multiply them and get 200 out of it. Now, in different courses or different topics, they do this thing differently. Like if you are in physics, those of you who have taken your physics 101 or something, what is the name that they give to this manner of multiplying arrays of numbers? What do they call them there? Close to that. It's not cross, it's something a dot product. This is actually, in physics, they do this thing and call it dot product. And what's the main use of it, or the first time that you use it? They use this to refer to what? What is it that they're trying to calculate that they do this thing with it? Yeah, you have one vector. Let me write some letters. Let me see if it rings a bell. You have one vector which has some components and another vector which has some components, and you multiply these 2 vectors, and that multiplication is called the dot product. And what is it that you get out of it? What do F and D refer to, and what's the output? Yeah, this is displacement. That's the force. Product of the displacement and force is, what is it that you get out of this? Oh, very good work. Okay, so very standard topic elsewhere, that you have vector of displacement, vector of force, you multiply them in this particular style, and what comes out of it is the work that you have done. So that concept 1,000,000 times more useful than this one is. Now, in physics class, they could write these things any number of ways. In linear algebra, we kind of insist on a particular format for these things. So let me call this one array of numbers, and this one array of, say, prices. I take my numbers and write it like this: 2, 3, 4. I insist the second one, 10, 20, 30. And the product of these 2 I consider to be 200. So if you wish to call this dot product, or so this is an example that in physics is called dot product. Now, what we are going to do is that the main view that we have toward matrix multiplication is that our matrices are made out of a bunch of rows, first one, and second one we are going to view it as a bunch of columns. And then we are going to go ahead and multiply them in this style as if we are doing lots of dot products. So our let me do an example of a matrix multiplication. Suppose I have 2, 3, 4, and then 5, 6, 7, and here I have a matrix of, let me not to leave the wrong impression here. Suppose this is 10, 20, and 30, and then 100, 200, and 300, then 1,000, 2,000, 3,000. I just chose some friendly numbers so we don't get bogged down with lots of calculations. So what is the idea? The idea is you view this as a bunch of rows, and you view this one as a bunch of columns. This is one way of looking at the board. There are other ways. And you do one row and a column at a time, and then you write it at a location that is inherited from the location of the row and the location of the column. So for example, if I call this row 1 and row 2, and this is column 1, column 2, column 3, if I multiply row 2 with column 3, where would I write my answer? So we are going to first keep track of where everything is going to go. 1 and 1, this is going to be result of 1, 1. I'm just going to indicate who is going to come there. We are going to specify later on the guy that's going to be there. 1 and 2, row 1 and column 2, we are going to record it here. Row 1 and column 3, we are going to record it here. 2 and 1, whatever it is, we haven't done the multiplication. Once you do it, we are going to put it down here. 2 and 2 is going to here. 2 and 3 is going to go here. So these are the locations. Now let's go ahead and figure out actually what are the numbers that are going to go there. We practice 1. 2, 3, 4, 10, 20, 30. The number that comes here is going to be what? 200. Is that right? That's what we practiced. So if you want to do it in your head, you say 2 times 10, 20. Plus 60 is 80, so forth. Plus 120 is 200 total. Can somebody tell me quickly who is this guy? All these numbers are 10 times bigger than those numbers. So this makes sense that this is also going to be 10 times bigger. Or if you wish, just do it individually. 200 plus 600 plus 1200. That makes it 2,000. How about the last row? I have 2,000, 6,000, and then 12,000. So I'll have 20,000 there. Now, can somebody tell me what is the number that shows up here? So again, that's the curse of linear algebra. We have to do a lot of arithmetic. So you say 5 times 10 plus 6 times 20 plus 7 times 30. That's the entry that's going to show up here. So it's a 50 and 120 and 210. So 330, and that looks like 380. Is that right? 380. Since we were forgiving on ourselves, I chose some easy numbers. I'm not going to have a hard time with that one. Okay, so this is one way of looking at matrix multiplication. So let me emphasize. So let's repeat again what happened. it's very crucial how you are laying things on the floor or on the paper. So we have a concept of a first matrix and the second one. We treat them very differently. On the first one, we are splitting it into rows. Second one, we are splitting into columns. Then each row is going to tangle with each column. The way we multiply these two is according to the dot product you might have seen in other classes. So corresponding entries are multiplied, then added. So it isn't just a multiplication, but you have a bunch of addition too. The net result of that is one single number. Then you have to do this thing over and over again, so typically a lot of work involved in carrying this out. Now, we said that with matrix algebra, you always have to watch out for compatibility. What is the compatibility requirement for multiplying two matrices? So let's, what do we want? We want there should be as many entries here as you got over there. Well, what are you counting here? This you are counting number of columns of the first has to match what? Number of rows of second. So that's a compatibility condition. Okay, once you have this compatibility condition, some matrix is going to be born out of this. Size of that is dictated by size of what you started with. Can you tell me what are the size of outcoming matrix? The number of rows of this is equal to what? Number of rows of your first matrix. And of course number of columns of it is equal to number of columns of second matrix. And so on. We can extend that idea to just so that we have a couple of items in case you come across them. If you in your exercises, we have something called the zero matrix. What do you think it is? It's all zeros. As many as it takes in a particular problem that you are considering. Sometimes they indicate how many rows and how many columns, but typically they don't. Also notice that when they write it in the text, they have the advantage of putting it a boldface, but I'm just going to write 0, and you have to understand from the context, is it scalar 0 or is it matrix 0? What do you think is to be understood by negative of a matrix? Negative of a matrix, so if you had a matrix with certain entries, negative of that simply means every entry has been made negative. So when you come across this type of concepts in the text for your exercises, you are clear about it. Now we need to talk a lot more about multiplication and other things. So section 1.3 is going to be a little bit lengthy. You want to go ahead and do the exercises from 1 through